So good morning, and we are going to start today about discussion on finite element analysis. That is different element types. Last time we have seen, and today we are going to continue the same discussion. So it was planned to have an answer session, but answers is not working on my PC. So that's the reason we are going to move it to some other aspects of finite element. So basically, we have seen in a different types of elements, like in a 1D element, 2D element, 3D element, and maybe higher order elements like in a polynomial P type approximation and H type of approximation. And there is a certain function which decides the behavior of finite elements. Behavior in the sense you may be giving some input to the system, it is going to determine, it is going to give an output. So we are going to have a connection between these input and output. What it is called as behavior, and that is what is represented in kind of in terms of some transfer functions. Okay, so that is what it is typically called as a shape function. So shape function means it is, in short, I can tell you one thing that shape function decides how the deformation is happening in the element or do within the element during whatever the within the element, that is what basically a function called as in a shape which decides the shape after application of load or kind. Then we will see some convergence criteria, and we'll see other things. So these are the elements we have seen: element number 2 noded element, 3 noded element, 4 noded element. So here, if I just show you one thing, if I take a note, two noded element, then typically this is what I'm a node. Here my displacement is in U1. Okay, here my displacement is U2. So this typically, if I want to plot it, this is my x coordinate. This is x coordinate, which is typically under that is independent parameter. Here it is in vertical direction. I'm going to determine u displacement at different locations. This is a displacement at node number 1 is u1, and node number 2, my displacement may be something u2. So this is the displacement we got, and this is another displacement. In finite element, what we have done, we have approximated displacement between this all the points. What is its approximation? This is nothing but a typically line you are going to join it. So then it is called as a linear element. What does the line? Line is nothing but a straight line, which is going to tell us about u is equal to some function of x. So this is what it is called as a shape. Okay, but this shape function is represented, okay, on the nodes, not on the entire element itself. It is based on the nodes. So now I can have this. I can divide into two parts. One is this is my one element. Okay, I will now concentrate on node number one. I'll give a maximum displacement to this. This is what it is called as one unit displacement. Reason for unit displacement, whatever the construction we have seen, for bar element, we have an element stiffness matrix is AE by L. Okay, 1 minus 1 minus 1, 1. Okay, if I am going to do a temperature analysis of something, so then stiffness matrix, that is what it is also called as a conductivity matrix, also will have a 1 minus 1 minus 1. So if I am going to do a torsion analysis or something, still I'm getting this, what are the constant, this what are the constants will be different. This is again some constant, this is again for some constant. I'll get in the same kind of a matrix. Okay, so likewise I can have such n number of different fields where I can apply a same kind of a matrix contribution. Only I'm going to change this. I'm going to change this constant, and I will have a different kind of an elements like. So this is what basically this is remaining common. This one, two, all the stiffness matrices remains constant, common, but their constants are going to vary, or their whatever the multiplication is going to. So what it happens when I want to keep it this is common, okay, only I need to change this. So how can I do it? So I can have a unique shape function for each node. So that's what I'm going to give in a one normalized shape functions. That is also called as a natural coordinate system. We are going to use it for this. So this is what in a normalized means for in a particular node. If I'm going to define a shape function for this, so this is what it is in a unit deformation I'm going to look at. That maybe in a deformation in displacement in x direction, y direction, z direction, anything it will happen. Another, that one may represent in a temperature also. That one may represent in a torsion, that is theta is also parameter. So that's what this is what in a normalized displacement. And whatever the nodes we have in another node, that is the second node, I'll assume that displacement is in a zero here. Okay. Now I can quite easily. This is what the shape is called as the shape function. That is what on a shape function for node number one. Okay. So this shape functions for node number one. Similarly, I can have another shape function for node number two, which is I'm going to concentrate it. So this is node number one. I'll give the unit displacement at this location, and I'm going to join this with a line. I'll get another shape functions. That is what I will say it is an n2 shape function for node number two. So if I add these two, so this is my n1, this is my n2. Okay. If I add these two, I'll get another one. I can sum at both the functions. Means ultimately I am getting some n1 plus n2 something. Ultimately I'll get a shape function like this. So this is my unit displacement for this. This is also unit displacement for this, and I'm getting some shape function in this fashion, number one and not. Whatever the variation in this is represented by a first equation, that is n1 plus n2 anywhere in the element. If I add up these equations, that will come to be the one. This is first law for the shape function. Okay. So second law is that this is for a normalized case. Okay. If I'm going to have a kind of something. Okay. So if I'm going to have something like a different case, like I want to have determine a displacement, what I can do it, I will have another equation that is taking care of these shape functions, but along with that shape function, it is taking care of the field variables. So that is what it is called as in a second law of the shape function. Okay, that is I can now n1 corresponding to displacement, that is u1 LC plus n2 u2, so that is total displacement anywhere in my entire element. I can quite easily determine displacement anywhere in there. So this is the way it is defined. The shape functions, its first equation for shape function is n1 plus n2 is equal to 1. Then second is n1 u1 plus n2 u2, which is equal to u now. Okay. So this is for 1D element. So this is the case for I can say for 1D linear element. So we will discuss this in more detail in natural coordinates when we are going to discuss about coordinate systems. So this is represented in terms of natural coordinate systems. We'll deal with some equations and we'll solve some problems. Okay. Now I will get a linear equations for this. So similarly, if I'm going to have a three noded element, this is my one node, this is my second node, and this is my third. So I will have a displacement here one, two. Displacement may be a one. Here my displacement u2, and this is my u. If I'm going to join these all the displacements, okay. So here I will get in a quadratic equation. Okay? quadratic equation, or I can say it is in a second order equation. Okay. So when we are dealing with the second order means I will have this u is a function of x, and that function may be a c0 plus c1x plus c2x. This is what in a quadratic, because power here this power is somewhere 2. That's the now if you are going to represent in terms of a shape function. Okay, so how can I define a shape function for node number 1? I can define a shape function. So this is node 1, 2, and this is my third node. I will have an n1 unit displacement at this, 0 displacement at another node, other all the nodes. So how can I join it? I can now join like this, and I'll get an. So this is my n1 shape. Similarly, if I go for a third, that is a second node, that is node shape function number 2. So here my displacement is 1, displacement for node number 1 is 0. Okay. For node number 2, as I'm going to define the shape function, here displacement becomes 1. Okay. And then rest of the nodes displacement is, we'll get this called, what it is called as the N2. And third one, that is what I can have node number 3 here having a displacement 1 unit displacement. This is 3 number node, this is 2 number node, this is 1 number node. How can, and now I need to keep the displacement for both those nodes in a 0. I can now join like this, and I'll get a shape function. Yeah. So for this shape functions, if I add all this is 1, 2, 3, all these three shape functions. I'll get the equation n1 plus n2 plus n3 is equal to again. This is my first equation. So if I want to determine a displacement at any point under this, what is the way I can do it? U is equal to n1 displacement of node number 1, n2 displacement of node number 2, and n3 displacement of node 3. So this is two equations. We can solve this and we will get in a all the constants of this equation. That is C0, C1, C2. We can get that. That is what it is called as in a shape function. Similar fashion, if you are going for a four noded, obviously this will one more term will increase, so that I can say C3 is equal to x raised to cube or something. If that is what, if I go on increasing the degrees of freedom, so that much number of orders of the polynomial I need to increase. That is basically theme line behind this shape functions. So we have seen here, this is what in a linear equation. This is my second order. This is third order. Likewise, I can go on increasing this. So what is the advantage you're getting? You're getting an advantage of this as I'm going to increase more and more order of my polynomial. Okay? As I'm going to increase the polynomial order, I'll get in a more accuracy. So that is basically idea, and that's what it is called as a p-type approximation. P-type approximation. Okay, so I'll give you one basically idea behind p-type and h-type approximation. Okay, I will have here h-type, and here it is I have a p-type. Okay, in h-type, if I have a bar, take an example of this is my bar, and I'm going to apply the force at this f, and I'm going to now divide this bar into multiple small sections. So this is one axis. I'm going to plot an x-axis. So this is my x-axis. This is my displacement axis. I'm going to determine the displacement at the location. This is my 1 point, then second point, then third, fourth. And so when I'm going to join this, I have a straight line connection for all this. I have an only straight line connection. That's what it is, a linear type of an element. Okay. So I'm going to reduce, I have only one parameter to control here. That is the length of my element. If I'm going for a more accurate type of analysis, I want a more accurate, what I have to do? I have to go for more number of points into this. This is what I can go on more smoother points, and I will go on in decreasing the edge size. This is my edge size. Previously, edge was larger. Here, the edge is small, and that's what it is. Edge you are going to control, and you are going to reduce this edge so that I will get in a better, can get in a better smoothness in this part, and that's what it is called as an edge type um, approximation. Okay, what is the advantage you will get the edge type approximation? If you look into the particular element, this is number of element, okay, in the particular model of the finite element, and I'm going to get an some displacement at a particular point. So this is the point I select. I'm determining u displacement also. U x I will say, or u maybe I will. This is my u. So initially I will get some value with a five number of elements. If I'm going for an increasing the number of elements, maybe 10, I'll get somewhere lower value. Maybe after that, maybe in a 20 elements, I'll get some value here. Like this, I can go on increasing the 100 number of elements, I'll get somewhere here. And after some time, so this curve becomes in a flat. So increasing the number of elements beyond this point is not going to or decrease or increase my displacement. So that is what this point is called as a convergence point, where I got a convergence. Merely increasing the number of points into this will not help us to get in more and more accuracy. Along with this, I can one more thing I can show it here. So that is number of elements, and I can have maybe percentage accuracy. So initially we will have a larger accuracy, and beyond certain limit, it remains constant. And this is the point where I will get a minimum accuracy, and below that I can't reduce it. That is what a finite element does. Finite element, what it does, it can give you approximate results. But what is the limit of approximation? This approximation maybe in a sometime 1%, sometimes 0.5%, maybe a 0.1%, depends on what kind of a model you're going to analyze it. So that is the basically advantage. That is what it is called as an element level convergence. But as we are going to increase more number of elements, okay, so as I'm going to increase more and more number of elements, what is going to happen? I'm going to increase more degrees of freedom into the number. As I'm going to increase more degrees of freedom, what you are going to do it? Obviously, you need to solve more number of equations. You are setting more number of algebraic equations, then your matrix size goes on increasing. If I have a five elements, five five noded model, I will get in a five by five matrix. If I'm going to 10, I will get in a 10 by 10 matrix. What the way you will increase the size. But as we are going to increase more and more bigger size of the element, so what is going to happen? That is going to take too much time for a computer to come when more kind of calculations. That is what it is called computational effort. So but from this point onward, if I am going to increase more my computational so will not affect my accuracy, and that is what then a limitation, and that is what it is. That is the point where it is called as convergence. In if you do some finite element analysis or something, so what is going to happen? This question comes into your mind. So how much the number of elements should be there? How much number of nodes should be there? So beyond that, I will not get and reduce, increase more accurate solution or something. That is the point. It is called as a convergence. Okay. So another point where we say it is in a p-type approximation. In p-type, what it happens, I have an element, my model. Okay, we initially took in only 4 points. Okay, I will connect with one linear element. I will say it is in a linear element. I'll get in a displacement at this point, and this point. Okay, this I am going to apply the force here and fixing here. I'm going to join this as it is a linear. The line between these two nodes is in a straight line. Okay. So if I'm going to use in a polynomial, linear means I'm using u displacement between these two nodes is my C0 plus C1 axis. So if I'm going to increase order like C0 plus C1x, C1x, sorry, plus C2x square or something. So then my displacement curve will have, I'm going to put up one node in between all the places. Means, so this is my one displacement, this is my second displacement, this is my third displacement. There is a node where I can determine a displacement. I can get in a one node. So here, so there are 3 points in the node, and I'm going to join these 3 points not within a straight line, but I'm going to have a certain curve, and that curve is nothing but a polynomial. So similarly, I will get another curve for this. Okay, and then third curve I'll get this. Means here only linear joining of the points. Here it is in a second order joining of the points. And the similar fashion, if I increase one more node in between it, okay, what will happen? I will get now this is my node. This is one node. This is my end node of the element. So I will have one more displacement here. Displacement. I will have how many points? I have one, two, I'll get 4 points as I'm going to join it. I'll get a third order polynomial. My equation of the polynomial equation will be C0 plus C1x plus C2x square plus C3x cubed. So similarly, I will get two more point in between it. I will get another. So this is the point where I'm going to have some other type of convergence. That point we'll discuss. So these are again another curve. What are the curve between the nodal points of the entire element? So this is third order polynomial. As increasing the only number of nodes within the element will increase your accuracy, and that is what type of approximation it is called as a P type of approximation. So there are trade-offs when you are going to increase P-type approximation. Elemental size increases, elemental matrix size increases. But in H-type approximation, your element remains same size, elemental matrix is same, but you are going to decrease the size of the element and getting more. That is what a difference between P-type and H-type polynomials. So this is what you can increase number of elements and kind of things, and you can achieve better accuracy. That was basically a theme line between P type and H type. So we have seen these all CST element, and the same concept is applicable for 2D elements and as well as for 3D elements. But in 1D element, it is quite easily you can visualize this all. But if it is an 2D or 3D, it becomes then when I'm going to do a 2D analysis, it becomes in a particular. If you take a simple example of 2D, I can just give that idea and then we'll move towards the next part of it. My x-axis, this is y-axis. This is my triangle I'm going to join. And four three nodes onto this. Here my displacement is u1, here I will get a u2, and here I will get a u3. As I'm going to join these all points, I'll get in some kind of on a plane, and that plane is a linear because this equation is somewhere a is c0 plus c1x plus c2y. So that is what. Order of this x or a1 is all the time 1. That's what it is a plane. So if I increase one more node in between it, just take an example of another element. This is y. I'll take these are the nodes. Increase one more node at the edge of it. So what will happen? I'll get displacement here, then another displacement, that's the third displacement. Within this, so when I'm going to join the line on the y-axis, so I'll get certain curve, and this is what the curve I'll get, and that curve is a curved surface. It's not the surface like in a planar surface like here, and that curved surface will be represented by a equation that is u is equal to c0 c1x plus c2y plus c3x square the C4 y square and C5 because I need to take in all the terms that is x, y, and all this. So how to take which terms are most important, which terms can be neglected. That point we will discuss in defining the shape functions. That is what it is called. Pascal stronger. So here, if my displacement is linear, and if I'm going to take a derivative of this displacement, I'll get a strain, and this strain displacement becomes a constant du by dx becomes constant, and that's what it is called as a constant strain because the strain within this entire element, anywhere in the element, remains constant, and that's what is called constant strain. If I look at this point, so that is a second order or something. So if I'm taking a derivative of this du by dx, equation of the strain becomes on a first order. Means it is a function of x and y. And this is what this equation is called as a linear strain triangle because whatever the variation within the element is a linear, with variation of the strain is a linear. That's what it is called as a linear strain triangle. Otherwise, you can increase number of element, number of nodes, you will get a higher order strain variation and kind of thing. Okay. So we have seen this part already. I'll just skip these slides and we'll move towards most important point, that is convergence. In convergence, I already told convergence means I have some elements like just try to understand all the finite element analysis based on 1D only because you are going to extend that part into the 2D and 3D same concept. This is what on a 1D I'm going to do. So I will get in a some displacement matrix that is 1. So here it is in a k 1 minus 1 minus 1 or something, and then another matrix I got it, and third matrix I got it. So here we have a displacement node number 1 and 2, 3 and 4. So when I look at the connectivity, this is my first element, this is my second element, this is my third element. So here node number, if I separate this particular element, I'll get a U1 here, and this is my U. And this U is nothing but sorry, K into U is equal to what are the force. So I'll get a stiffness matrix which represents this equation is my displacement of node number 2. Okay. And similarly, if I look at second node, this particular equation, that is the first equation, represent displacement of again node number 2. But this displacement, this U2 and this U2, both are the same. And I need to keep these two things the same in my analysis. Otherwise, what will happen if I am going to plot with respect to x? All this displacement. This is my fix. If I fix it here, I'm going to apply the force. Just look at here. I got a zero displacement. Here I got a displacement u1 on the element number one. And if I get another u2 or something, here it is now u1, and here I got a u1. Sorry, u2 on element number one and u2 on element number two. I'll get this another. What will happen if I'm going to join this? I'll get a sudden change in it, which is not accepted, not there in all the practicals. So that is the reason these two should be the same, and that's the reason this is what we are going to add it up all these equation, and I will get an assembly of it. This is what on the first thing, wherever it is coming common nodes, common nodes. So displacement of these nodes should be the same or they should be added up. And that is what you are doing in a first thing. That is a C0 type of an approx conversion. Why it is called as a C0? U is my field variable. Okay? U is my field variable. हाँ बोला मॅडम काय अर्जंट आहे का? हो माझं लेक्चर चालू होतं. लेक्चर अर्ध्या तासात होईल. हं. So here I got an displacement. U should be the same. That is what an optical is. And that's the this is my field variable. If I took a temperature as a field variable, I will get an a T. If I am going to do an a CFD or something, I will get an a V, velocity of my particular flow, velocity of particle or something you can say. If I am going to do an some temperature, other type of analysis, that field variable comes. Order of this differential order of this particular is 0, 0, 0. Okay. So I'm going to match the displacement of this U2 and this U2 on particular node, and that's what it is called as a zeroth order differential equation. That's what C0. Okay. So now we look at if I'm going for some another type of approximation. Take an example of bending beam. This is my beam having these many elements. This bending of the beams. So now it is not on a bar element. I'm going to apply a transverse force. When I apply a transverse force, that indicates beam type of a structure. Okay. So obviously these nodes are having now displacement in this fashion. So it will displace in this fashion. Okay. If I look at this, so this is my one number node, this is second, my third, node number one, two, three, and four. I'm going to determine two things into this. One is vertical displacement. Here it is a zero. I will have some displacement u1 here. Here I will have u2 displacement, and here I will have u3 displacement. Okay. So when I'm going to match this U1 and U2 and U3 at common nodes, these are the common nodes, 2 and 3 are common. Then it satisfies C0 type of continuity, or also called as a convergence. So another one, when it is rotating, what is going to happen? So displacement of first node is here, displacement of second node is here. I'm going to join this with this. So for third number node, I will have a displacement. I'm going to join this one. So slope of this point and this point is in a different. If these two are different, obviously I can't get in a smooth displacement over the entire model. And that is again creating a problem. So that's what if I take a theta angle here, theta is not with the slope for it. I'm going to now match this theta also onto this. I'm going to match this theta on this node, this theta on element number 1 and element number 2 are matched, and theta is nothing but my strain, that is du by dx, and order is here 1, and that's what it is called as a C1 type of continuity. Okay? Why it is called as a C1 type. Okay? That is here you are going to match this du by dx, matching the du by dx of the element number 1. I can now have a du by dx of node number 2 in the element number 1, and here it is a du by dx of element number 2 at node number element number 2 at node number 2. So you're going to have saying that this is both are same, and that's what it is called as in a C1 type. Otherwise, what will happen? I will have an a C1, here I will get an theta 1 somewhere, and here I will get an a theta 2. And that may not match these tangents out. And these tangents, if they are not matching, I will not get in a proper smoothness on it. And that's what this may get in a fail. And this type of continuity is also most important in the case of FEA analysis. Third type of continuity is that is a second order, that is a curvature. If I take in a plate like in a structure, this is my plate. So when I'm going to bend that plate or something, if I'm going to fix it, this plate at this both the end, and I'm going to apply the force on the center force. So this plate is going to bend it in this fashion. Okay. When it is going to bend, you may be remembering the slope, what are the curvature, and then that may be somewhere at the center. So that is curvature is represented by d2u by d. I'm going to do an only 1D analysis. And same, if I'm going to do an, a 2D analysis, then it becomes a d2u by dy square. And if I'm going to do an, a 3D analysis, then z also comes. So if I'm going to look at only one direction, just look at whenever you do an analysis, my request is that first of all, only concentrate on one direction. And then same is applicable for other directions in 99%. We, if you are considering anisotropic or not isotropic and taking into account, then that will be something different. So if I look at this, so curvature at this point, if I consider this is my one element and this is my another element, curvature at of element number one, this is element number two. At this point, it's same as curvature of the element number two of this. So then it is called as in a second order. It is a second order equation, second order to displacement in the displacement. And that's what it is called as a C2 type continuity. And that is, it is mostly it is applicable in plate type of structures. Okay? Plate and beam bending analysis we use. So in this case, you may be remembering that as d2y by dx square, which is equal to minus m by e. So this is nothing but a beam bending equation. And this beam bending equation also came from this is curvature. And the same is here also. So don't get confused with this. Something different. Both are the same. This is dealing with a beams. This is dealing with a plates. Okay. So this is what on a second order continuity. So this is what on a continuity requirement. First convergence criteria is function should be a continuous and differentiable. Able to differentiate that particular function in multiple times. That is what is called as a differentiable. And continuous means it should not have a sudden change like in a friction kind of behavior. If I consider a friction on the surface, so in forward direction I will have some different value. In reverse direction, the force direction remains. I mean, get changes into the negative side. So that should not happen it whenever we assume in a certain function within that element or that is a convergence first convergence. Second convergence criteria is displacement polynomial should include constant term. So constant term will help us in different aspects. In constant term, so if I am going to apply the force on the beam at fixed, if I am not considering constant term in the my polynomial, constant term means u is equal to a displacement is zero plus an x. Like this, we are assuming. We have not taken account of this. Only my displacement field is c1 x. What will happen with this? If I don't take this c1, c0 as a constant term into my polynomial itself, my displacement, if I'm going to apply the force here, F force, and okay, so then if I'm going to observe the displacement of this particular element, I'll get a displacement of this is 0, this is somewhere I'll get this displacement I'll get. This will have the same displacement because you are not going to apply any displacement. Get this? Actually, your displacement pattern looks like this. If it is not if you are not taking a constant term. So no constant term. Then your equation, your behavior of the displacement with respect to x shows like this. So this is what it is a rigid body displacement should have. It means this these two elements are not deforming at all, but still they have to move on without deforming to the next position. That is what it is expected. But it is not going to happen because you are not taken account of this constant term. If I taken a constant term, what will happen? And if I taken a constant term, my displacement pattern, this is my x, this is my u, and this is my displacement, this is my second displacement, and this is going to take care of this will take in a some curve. Will after that it will show you that particular rotation also will take an rigid body displacement will also, and that is going to happen due to this constant. And that is most important. You need to have each and every term into your polynomial whenever you are going to select a safe function. But this constant term has its own importance. Don't miss this constant term from your polynomial whenever you are formulating any elemental equation. So that is shows in a rigid body displacement. So second is then next there should be a similarly linear term. That is linear term means I can have u is equal to 0 plus even x. So this is what in a linear term. If I'm not taking at the C1, what is going to happen? Obviously, if I take a derivative of this du by dx, my C1 is coming. So what it indicates, I will have a frame which is equal to C1 over the entire element. That is somewhere we are going to miss it. And that is going to again affect my entire analysis. That's what to take care of constant strain within the element, I need to have a linear term in my shape. So next is compatibility. Already we discussed, and that should satisfy the geometric isotropy. Then it should be symmetric in all x, y, z coordinate. Okay, that is what it is expected that equation. So when we are selecting the terms into the any 2D element or 1D element. So in 1D element we can go on have an only x terms. 1D, my shape function is u is function of only x. That is one. For 2D, I have a shape function which is function of x as well as y. Okay. And 3D element, I have a shape function should have u is equal to function of x, y, z, others. When we need to take care of 1D analysis, means we can take a C0 as a constant term for rigid body analysis, C1 for constantly, that is a strain term, I can say, then C2, like this, I can go on increasing. But when we are going for a formulating for a 2D element, I need to be taking care of all these terms in the my equation. So for that purpose, I should have all the terms, and for that purpose, there is an triangle which is called as a if I'm going to analyze in a triangular type of an element, rectangular, in only linear equation, what way this is what in a Pascal triangles will have. So this is what in a constant term. This is my linear terms. These two are linear terms. These three are quadratic term because if you go on summing all the power of this two, that's what it is called. Similarly, these are the cubic terms. Then सर जी लेक्चर चल रहा था मेरा तुम्हारे स्टूडेंट को बोलो कि इमीडिएटली वो ज्वाइन हो गए उसके जो ऑनलाइन कोर्सेज थे ना उनका रिव्यू ओके 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 मैं 5 मिनट में मेरा लेक्चर ठीक हाँ So here we are going to have a different terms in this. If I'm going to formulate an one equation, let's just look at it, a triangular element with a linear equation. So I can have a C0 as a constant term. I need to take all the terms above this. Then it is called as a linear. C0 plus C1x plus C2. What my linear terms. Then if I'm going for an quadratic, I have to consider this is what the line. Above that, all the term I need to take. I need not to miss any of the term. This I am going to write C0, C1x. So I'm going to take this two, C2y. Then I need to take all these three also. C3 x square plus C4 y square and C5 x. If I'm going to define an element within a cubic variation, I need to take all the term above this line. Then I can have u is equal to C0 plus C1x plus C2y plus C3x square plus C4y square plus C5xy, and then this cubic terms, that is C6x cube, C7 x square y plus C8, 7C8 xy square, then C9, like this. So likewise, I can go on defining my polynomial equations. For that purpose, this. So this is what for fourth, I can take these many. Okay. For linear term, I have three terms into this. Quadratic 3 plus 3 it becomes 6. Cubic term 6 plus these 4, 10 terms. Like quadratic increase, like way whichever you. That is what the way Pascal's we use for defining 2D elements. Similarly, if I'm going to define 3D elements, then it becomes a tetrahedron because I have to have on a 3D means I have on a x term, y term, and z term. If I'm going to define in a linear equation, so I have to take in a 1, 3, and 4. So I can have on a constant term C1x, C2y, then C3z. So this is what about this. All the terms are taken, then it becomes a linear. So similarly, if I want going to define a quadratic, so I have a constant C0 plus C1x plus C2y. So this is from the linear. And for quadratic, I have to take all these terms, about terms, this line. So I can have a C3x square plus C4y square plus C5z square. Here I miss this something z, and all these terms should be taken into account. So I have to take an all together. Here it is in a linear term. I have 4 terms. Here it is in 1, 2, 3, 4, 5, 6, 7. 7 plus 4. Then I will get in a 12. That is 11. If I'm going to have a quadratic equation. That is the basically understanding about how to take in a polynomial analysis. If you miss any of this term, obviously it will affect into your analysis, and that may not reflect on a perfect behavior, practical behavior of your analysis. That's the reason we need to take care of all this terms. So if you are going for an hypercube also it is there. So that way you can go on doing all this. Okay. And one more thing I will explain and I will finish my session today. So this is nodes are selected in the points. That is what and wherever you want to determine an unknown. That is at which basic unknowns, maybe displacement in elasticity, temperature in thermal analysis, to be determined in finite. Okay. The basic unknown at any point inside the elements are determined using approximately linear function. Means if this is my element, I have a displacement I have determined here. This is my U2. I want to determine the displacement at some x point. What I can do, I can approximately join these 2 points and I can now determine based on interpolation between these 2 points. That is what the approximation. So that's what we are using this interpolation and shape. And there are two types of nodes, maybe an external node. So these are called as an external node. If I'm going to put up one node here, then it is called as an that's it. It's not a more meaning for it. External nodes, which occurs at the edge of the surface. That's what it is called as an external node. So these are 1 and 2 are external node and 3 is my internal node. Okay. So